President. And I would also like to thank Professor Young, who kindly invited me. And this is my fourth, well, I've been to before, yeah, visit to Hong Kong. And every time it's perfect. Weather is perfect. So this has to be one of the paradises in the world. So I envy you people. But in the meantime, my hometown is near Chicago, where a bitter winter must have already arrived. But sometimes I feel that this harsh environment can even foster our scientific curiosities, the kinds, something like that. So I have to think that way anyway. So beginning. May I start my lecture? Yeah. Okay. So this is one of relatively rare occasions where I should discuss chemistry, but not in chemical terms so much. So I try my best. Okay. But there is no question that chemistry is extremely important. We all are chemical, biochemicals, and we need chemistry. So first 10 minutes or so, I would like to discuss how I may have won a Nobel Prize with what. And that's, you see, it's hard for me to see while I stand here. Oh, okay, yeah, that's better. Okay, so here you see two diagrams, and the one on the left is the one that gave me and some others the Nobel Prize in 2010. So let me just briefly explain. And may I have a pointer? Yeah, okay. Pointer should be pointed, pointed this way. Yeah, okay. Okay. So this is the scheme for the so-called Negishi coupling, or including some others like Suzuki came along later, and Stille passed away, but he developed a method primarily depending on this tin. And what I want to show you with this scheme of cross-coupling is a few things. First of all, how I came up with this kind of cross-coupling. Cross-coupling was already known, but it was not widely used, not widely known. Okay, and my notion was that, okay, so this represents the great majority of organic compound, great majority. And we ourselves are organic, or any animals, any vegetables, and food items, and drug items. I am taking, my doctor says I should take two kinds of drugs. One is called losartan, blood pressure controlling medicine. So I looked at the structure. It's a kind of biaryl. Two aryl groups joined together. Maybe I can make this one with my method. It's a joke. The companies are already making losartan using my method. So they are already using it. And then more recently, my doctor said, you should take this medicine. It's called tamsulosin. Okay. I don't tell you what it is, but the same story. So if something is good, others bound to use it, and I think this gives me or my colleagues and so on a great pleasure and great satisfaction. And I'd like to talk about that. So here is the cross-coupling scheme, and organic compounds represent, synthesis of it. Heart of it is to form a carbon-to-carbon bond, R1, R2 carbon groups. So there's a little bar here, that's a bond. So this is organic compound. How do we make it? And when I was 26 at the University of Pennsylvania, I was a darn good student in first year. Second year, I was a miserable experimentalist in my own PhD research. And I said, why is organic synthesis so complex and difficult and so on? Then at that time, from Netherlands, not the Netherlands, but Denmark, I think, the game called the Lego game. Lego game invaded America, along with the Beatles from UK. Anyway, so you know the Lego game. In the Lego game, you have a piece 1, piece 2, and then if they are the same sort of appropriate shape in the critical part, then all you need to do is just to snap it. Then you can get this one. And this way you can make anything. House, airplane, and so on. Whatever you want to make, you can use Lego game to make. And I thought at the age of 26, isn't it nice if we can synthesize organic compounds in this way? And indeed, that simple, naive notion gave me this approach, and then eventually I developed, or we and others, I should say. So here is what we want. So Lego game piece 1 is R1, and put X electronegative element like halogens. So that will pull electrons from R1. So R1 becomes R1 plus, essentially R1 plus. And then the other piece we need, we put metal. Metal is electron donating. It wants to become plus. So that will make R2, the other partner, negative, R2 minus. So Lego game with a stick. And if you snap these two, then you get this one. But how to snap it, the two, in chemical world, that was the thing. And then we learned that we need a helper, catalyst. So this green frame. And turned out that this helper should be so-called transition metals. There are a whole bunch of transition metals in the periodic table. But today I won't explain too much. Anyway, so this helper is here, and then it will go in between R1 and Rx, so as shown here. So this X is minus, metal is plus. Now, if these two come together, then plus, minus, this formation of Mx gives a tremendous driving force. And then R2 replaces X, and then you get this one. Now you see two are captured by transition metal, such as palladium. And then these, I will explain a little later, these transition metals have a tremendous, very fantastic property. So they can go up and down, adjust so-called oxidation state. So here it's zero oxidation state without any ligand, so-called nothing is attached. Here with the two groups, two R1 groups, and R1 is more, well, metal is always more electropositive. So these are two negative groups. But these two negative groups can be bumped into each other by M, and then M will leave, and R1 and R2 get coupled. This is the essence of cross-coupling. Okay, and the important thing is that this M started in this form, then now in this form, and then when it spits out what we want, it goes back to the same species. This is the essence of catalysis. Because it can go around and around and around. How many times? Twice? No. 10 times? No. We typically ask this transition metal, such as palladium, to go around 1 million times or even more. Palladium is one of the most expensive metals. So people think of palladium, why do you use very expensive palladium? But even if palladium costs $1 million per mole, which it doesn't cost that much, but even if it costs $1 million per mole, if it turns around 1 million times, actual cost is $1 a mole. Sorry, American slang. $1. Almost nothing. So this is the beauty of, or charming part, attractive part of the catalysis. In other words, because catalyst doesn't die, catalyst starts here maybe, doesn't matter, any place it can start. Took us 17 long years. Came up with this reaction in 1995. I call this a post-Nobel research work. I'm very, very proud of this one. Next one. Next one. So clearly I don't have time to go through this one. Yeah. Let's go to, okay, let's go further. Okay, further. Yeah, I will go further. Further. More, please. Yeah. So all these compounds. Only difference is that in this case, methyl in this configuration, if you put it this way, this methyl must lean towards you, not away from you. You know, that's the only difference. In this case, this thing is pointing away from you. Anyway, and sometimes the difference is, look at this one. You may have seen this isotope, deuterium isotope. Look at this one. In this molecule, after this branching point, this branch is CH2, CH3. This branch is CH2, CD3. So only difference between the two is isotope difference. Difference by isotope. We call this isotopomer. So these are extremely difficult to synthesize. These two look similar, but it's different in this orientation. Isotopomer. Okay, next slide. No problem. We have done it, and in view of time, I will just say we have done it. It's a terrible thing to say. And so when we synthesize these things, we usually use optical method, rotation measurement. But those things eventually became useless. And not always, but mostly useless. The only thing that survived was a more modern technology called NMR. NMR is the only tool, but even this NMR was in danger. But to make a long story short, we can tell the difference, and I will show the results. Next slide. Next one. Next. So, and by using NMR, we can tell. Okay, next one. So here you see we have this CCSI. At this point, one is a C. This bent is a CH2, CH2, So this one is a CH2, CH2, deuterium and hydrogen difference, far away from this branching point. And as I said, optical method, we couldn't detect the difference. Okay, no NV means no rotation. Optical method is no. Then we need to seek a better analytical method. Turned out that the last bastion, last rescue, came from NMR. Next slide, as you may know, NMR. So when we have this kind of thing, it's very difficult to tell the difference between this one and then the wedged one. But if you have a mixture of one-to-one mixture, we can easily synthesize one-to-one mixture. Then by NMR you can tell. So you see 2, 2, 2. If it's pure, then it should be one of these, one of these, one of these. Okay. So we made a pure one. Look at this. Look at this. So we don't have this one, hardly any. This one is further away. We don't consider this to be a part of this one. We don't see this, we see this. Sorry, I'm looking at the wrong angle, so I may be off. But in this case, we don't see anything at all here, just this one. And this one only. So, in this way, we can tell that this is very, very, very pure. So now we can synthesize these kinds of compounds very pure. Why is it necessary? As I told you, many drugs, they have these chiral property. And small amount, like a ppb, ppm, ppb level of wrong isomers can act as a toxic. So we must maintain. I checked with a couple of pharmaceutical company colleagues, and they said most of the time ppm level is okay, but that's not safe. If you jack it up by one notch, ppb level, then you are pretty much safe. Okay, so this is where these things come into play. And of course, I'm not discussing that how to make them, but we can make these things that pure. Okay, next one. So pretty much, I'm sorry. Next one. Next one, please. Okay, so Yeah, recently we synthesized. Okay, this one is simple. Next one. Okay, this is the one. This was a real contest, worldwide contest. One came from the Netherlands. 27 steps to synthesize this particular compound, which shows up here, here, and here. Here, sorry. These are similar, but OH. 27 steps. Overall yield 2.5%. Too long. Almost all, 97.5% of the materials wasted as production of the wrong product. And then came a very powerful work from Switzerland. 20 steps, 15%. Wow! At this level, they can make and sell and can be beneficial to the mankind. But still, we were concerned about 20 steps. But of course, in the meantime, we were busy doing it. And we are the most recent one, but look at this. We can synthesize this compound, thioceranic acid, in 8 longest linear steps, compared with this one. This 8 is amazingly efficient. Well, of course, we lag a little behind the Swiss group here, but 8% overall yield is still okay. So we are undecided which of the two is the best. We like this combination, but it's up to the rest of the world. So now we can not only synthesize, but we can detect, we can analyze, and I call this conquering the last bastion in the synthetic chemistry. Next slide, please. And I think with that, so this just shows how pure we can tell how pure this compound is. Very, very pure. Next slide. Next slide. Here again. Yeah, okay. So I'm sorry that I have put you through these very highly professional chemistry, but I hope you got what the catalyst is all about, and so on. And so over the years in the cross-coupling area, many people have worked. Next slide. Sorry. Yeah. And in asymmetric synthesis that I discussed briefly, using a zirconium, first this brilliant and a little crazy boy, Van Horns, came up with nice work in 1978, and a bunch of us struggled through to come up with the finally desirable thing. And eventually, 17 long years later, a genius from Russia, he won the Science Olympiad, as a youngster. I think these kinds of people have something really special. So he discovered, almost single-handedly. I was busy traveling already. Anyway, next one. So more recent one. Many people from big country of China, as you can see here, and some from Japan. My old company, Teijin, kindly has been sending some of the best people steadily, to which I'm very thankful. Next one. Okay, one of the most recent group photo, very small group. So they made me not a living statue, but I still want to live and do more. Thank you very much.
Thank you, Professor Negishi. Please stay. And may we now invite Dr. Shelley Yang to come onto the stage to present their certificate of appreciation to Professor Negishi.